So, hi everyone. I have to first totally apologize for what happened this morning. That is really, really unusual. Let me just explain that. So I was on call for 24 hours at the hospital on Thanksgiving, and I had the worst 24-hour call period I've ever had in the 18 years I've been here. I literally worked the entire time. I ate my Thanksgiving dinner standing up at 9:30 p.m. Running to check on a patient every minute to go make sure they're okay. It was not a very happy thing. So I don't usually sleep the following day because if I do, then sometimes I have a hard time sleeping that night. And I'm on call again tonight. So I took a sleeping pill last night and I slept from 10 p.m. until 10 a.m. And I just never dreamed I would do that. So that's really unusual for me. So I apologize that you guys were sitting there waiting for me to turn up and I never did. I apologize. The first thing that this shows to me is that we need a better way of communicating because I can't email into the Valley School system. I just can't do that. And it blocks me out. So the only way I can communicate you guys right now is to email Amy and then have her email all of you, and that's not a great way. So I think what I've done in the past is when I've also taught physics online, and what I've done is I've had a WhatsApp group, and I can just text WhatsApp links. I can text, if there's a problem, I can text that to people. I can communicate directly. And if that's okay with Miss Amy, that's what we'll do. If it's not okay with Miss Amy, we'll have to figure out something else. But that's the best way I've figured it out in the past. This where I completely miss it has never happened before, but there are times when, for example, next Saturday I'm on call again. It's one of these low priority calls, not like Thanksgiving Day where I have to be in the hospital, and I knew I was going to get slammed, although I didn't think I'd be slammed that much. The one next Saturday, it would be like either I'm okay and I'm not having to go in, or it may be that I have to go in and cancel, but I would know in advance. And so sometimes I say, okay, look, Saturday is one that I might miss. So but I'll let you know ahead of time. So, look at your WhatsApp at 8 o'clock in the morning, and it may be that I say I can't be there, but I may not know that until the morning of. Or sometimes, like if we go in the evening, I'll say, hey, it looks like my schedule is going to be okay for us to go at 6 o'clock, but I never know when I'm going to get done until I walk out of the hospital. So it may be that at 4 o'clock we're running behind and I have to text you and say, hey, gosh, I thought it was going to be done at 6. It's not going to happen. We'll have to reschedule. So that's why having a direct communication with parents would be really, really handy, because my schedule is just such that, unfortunately, most of the time I have a pretty good sense when I'm going to finish up and if I'm going to be available, but not always. And every once in a while, that's going to happen, something like this, although not where I just bail and don't even tell you. Okay. So I just got a text message from someone in this group. Okay. So let me tell you a little bit about MathCounts, because I'm pretty sure that not many people who are here are familiar with MathCounts. So MathCounts is this nationwide competition that's broken up into multiple sub-competitions. So in the past, I've taught MathCounts, I've coached MathCounts every time I've had a kid in middle school, and I've had a lot of kids in middle school. So Jonathan is now my 5th kid who I've coached in MathCounts. In the past, they always had a local, a state, and a national competition. Nobody I've ever coached has made it to nationals, but all of my kids have had a team that's gone to state. And then this year they're having something a little bit different, and I don't know if it's because of COVID, but they're having like an initial local competition, and then the winners of that go to the main local competition, and then the winners of that go to state, and then the winners of state go to nationals. MathCounts is a great organization. They have lots of educational materials. The local competition is sponsored by some mechanical engineers, and I think this is pretty unusual nationwide, but they provide amazing prizes. So kids that I've coached have won laptops, they've won iPads. One of my sons won a PlayStation, which we were not happy about because up until that point we had not had a gaming system in our house, but we couldn't very well deny it to him since he had won it. So anyways, I'm kind of kidding about that. But so there's great prizes. I can't promise that there will be prizes this year because of COVID, but it's a lot of fun, and you can compete when you're in 6th, 7th, and 8th grade. We always have a great time. This year will be a little bit different because we won't be able to meet in person, and the competitions won't be in person. They'll all be online. The interesting thing about MathCounts is it's never straight calculation, which I alluded to in my initial email. There's never, 67 times 42 or anything like that. It's all logic based. It's the setting up of the problem in your mind that is the important part and what they're testing. And the cool thing about that is that it teaches you how to think. A monkey, I don't necessarily mean this, but anybody can learn the skills of calculating. Okay, it's like, okay, step A, step B, step C, step C. The kind of problems you get in MathCounts are cool because you can't teach anyone how to do those problems because they're different every time. All you can do is teach people how to think about problems. And so it's actually sponsored by a big company called Raytheon, which makes defense stuff, but it's also sponsored by a sub company that's called The Art of Problem Solving. And that's exactly what this is it teaches you the art of problem solving. I can't teach you, how to solve any individual problem that's going to come up because they're always going to be different, but I can teach you how to think about problems in such a way that you can work through what the information you have and see how it connects the information that you need and how to think about that. So we are going to go through, since we only have 2 people here, we're only going to go through a few problems today, but I just want to give you a sample of what you're going to be looking at if you decide to do MathCounts, and then you can decide if that's for you. I'm just going to also mention that you don't have to compete if you don't want to. You're welcome to come to practices. I think it'd be great for you. I truly believe that my sons that I've coached have become better thinkers because of this. And if competing isn't your thing, you don't have to do that. You're welcome to join be a part of the competing team if you like, but you don't have to. Okay. So with that out of the way, and with the one more apology that I'm sorry, I completely slept through this. I'm really sorry about that. Let's get started. Okay. So what I want you to do, in the future, what I'll try to do is I'll try to send some problems to you that you can work on during the week. And here's the thing, you can tune in on Saturday and you can listen to me talk about a logic skill and you can watch me solve problems, but that's not going to make you great at MathCounts. It's not going to make you a great thinker of your own. It'll help. But what you really need to do is you need to practice doing problems that you haven't seen me do. And if you practice them, and you can say, if you solve them, that's great. You've learned how to solve a problem. You've learned how to think through a problem. If you can't solve them, you can think to yourself, when I solve them and show you how to do it, you can be like, wait a minute, okay, this is where I went wrong. I forgot to think outside the box. And a lot of times, that's what the problem is that you forget to think outside the box. That's an expression. It means you confine yourself to rules that aren't actually there. And in the first problem that we're about to do, I actually got it wrong my first time because I didn't think outside the box. And then Jonathan said, no, actually you can do this. And I'm like, oh, I put this rule on myself that I didn't need to. Other times you'll simply read the problem wrong. And one of the things I'll teach you over and over again is you read the problem, you read the problem a second time, you read the problem a third time, you solve the problem, you read the problem a fourth time, you read the problem a fifth time. And you'll realize if you take the time to do these problems before we meet, you'll realize how many times you'll get tripped up by not reading the problem correctly. MathCounts is notorious for wording problems in such a way that if you don't pay attention to what you're doing, you answer the problem that you think you're supposed to answer and not the problem that you're really supposed to answer. Okay, so just a plead or an encouragement to read the problem, try to solve the problems ahead of time. Okay, so let's do our first problem. I want you to look at a figure here. Okay, so you see this figure here. It's 2, 4, 6, 7 hexagons, and they're clustered in a circle, sort of, around the number 1 hexagon. And I'm going to draw that on a whiteboard, but it's not going to look as pretty as that. So when I draw something on the whiteboard, I want you to be picturing this right here, okay? So the problem is this. In the figure shown, if no cell may be visited more than once, and not every cell must be visited, how many paths start in cell 1 and end in cell 7? Okay, so let's now cut to the whiteboard, which I hope works. Let's see here. Where's my whiteboard pen? Okay, so we're gonna go to whiteboard. There we are. Okay, so I'm unfortunately a horrible artist, so I'm not even going to try to make hexagons. I'm going to make circles. Oopsies. And did I mention that I am a horrible artist? I think I did. Let's try this again, because I was watching the screen instead of watching what I was doing. There will be some technology glitches. All right, so now we're going to go back to draw. Okay, let's try this. I haven't done this. I haven't taught using a whiteboard for a while. Oops, that's clearly not what I want. So let's try this. Oh, I see that's the one I want. Okay, no, is that circle? Okay. Here's my first hexagon, and then I've got to have 6 hexagons around it. So I'm going to want to go like this, 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 and this. Okay, so you can see why I showed you the picture first, because this is really horrible. But it is what it is. Okay, so I'm going to number these 1, 2, 3, 4, 5, 6, and 7. Okay, so the problem states when you start at 1 and finish at 7, how many different paths are there? Now, I'm not going to put anyone on the spot. Jonathan's already solved this, and Bailey, I don't want to put Bailey on the spot because she's the only other one here. But so I'm just going to tell you what I did. Okay, so I assumed that you had to visit all of the hexagons. I didn't read the problem carefully, which is why I tell you you've got to read the problem 5 times. And I'm serious. And people make fun of me, and by the time they do their first MathCounts test, they're like, okay, yeah, you got to read the problem 5 times. So I didn't pick up the first time on the fact that you don't have to visit all of them. So I said there's only 2 paths. I said there's this one where you go 1, 2, 3, 4, 5, 6, 7, and there's this one where you go 1, 6, 5, 4, 3, 2, 7. There's only 2 paths. Okay, that's not the right answer. Okay, because it doesn't say, it specifically says you do not need to visit all the hexagons. So once I knew that, I said, okay, well, here's the way to do it. I can start at 1, I can go 2, 3, 4, 5, 6, 7. That's one path. I can start here, I can go 1, 3, 4, 5, 6, 7. That's 2 paths. 1, 4, 5, 6, 7, 3. 1, 5, 6, 7, 4. 1, 6, 7, 5. 1, 7, 6. Okay, so I've got 6 paths so far. Now I can go in reverse. Okay, so I can go 1, 6, 5, 4, 3, 2, 7. That's 2. I'm up to 7 now. 1, 5, 4, 3, 2, 7. That's 8 paths. 1, 5, 4, 3, 2, 7. That's 9 paths. 1, 3, 2, 7. That's 10 paths. 1, 2, 7. That's 11 paths. Now I've already done 1 to 7 directly, so I can't do that one again. So 11 paths is the correct answer. Okay. So first thing I want to point out here is that, as I've already demonstrated, not reading the problem will kill you in math counts. And that's probably a good lesson for life, right? Because no matter what you're doing, if you don't follow instructions, you're not going to get it right. So math counts, the first thing they test is, are you able to read and comprehend what they're asking and understand? And instead of putting in what you think you're supposed to be answering, are you careful enough to understand what they want you to answer? Okay. Second thing I'd like to point out is we did not do any calculations here whatsoever. This was all pure logic and thinking outside the box. And so people ask, well, what does that have to do with math? Well, in real life, math isn't about doing a calculation. Like, I don't have anyone ever show me, ask me what's 37 times 22. Nobody ever asked me that. But it's trying to understand a problem, and sometimes you'll have to use, math skills to solve that problem, but it's not primarily about calculation. Calculation is a foundation that you have to build on in your life, and that's why Math Counts is so great, is that school will often give you the foundation, but something like Math Counts really helps you to build on that. And school does that as well, but I mean, Math Counts really does that. Okay, so let's go ahead and erase this. There's also a way for me to clear things. Liz, where? Right here?
There, yeah. Clear all drawings.
Perfect. Okay, let's go on to the next one. This one I'll actually be able to draw because I'm not that horrible at drawing something like this. So let's see here. Let's clear the whiteboard. Actually, I'll just draw this because I can do this. Okay, so the problem gives you a rectangle. I did that okay, didn't I? Oops, why did it do the whole thing, I wonder?
Because you did it in one thing.
Oh.
So it erases what you've drawn until you looked at your pen.
Oh. How do you know so much about this?
Lots of Zoom.
And then there's a diagonal from B to D. Now, you may or may not have taken geometry, but I think you'll know how to solve this problem. If you don't, then you're going to learn something today. Okay, so the problem states, if the perimeter of rectangle ABCD, okay, so if you haven't taken geometry, by convention, whenever you're describing something, you name the points that are part of that thing. So here's a rectangle. It's rectangle A, B, C, D. Okay, so if that perimeter is 34, so we're going to say, I'm going to make this little box here, which means perimeter, and it equals 34. Okay, and AB equals 5 centimeters. Okay, what is the perimeter of ABD, of the triangle ABD? So we're trying to find the perimeter of the triangle don't let me erase this whole thing, Liz. I don't want clear. Oh, Jonathan's raised hands. Jonathan, what do you have to do? Sorry, what do you want to say?
First of all, I was saying, when I was giving you the problem, I was talking about the one below it, but like, we can do this one, but I'm just saying, aren't we gonna have to use the Pythagorean theorem?
Yeah, so people will learn. Oh, I see what you're saying. You were saying the one below.
Yeah.
Okay, well, let's do this one and then we'll do the one below.
Okay.
Erase and then click on the B and it'll erase the whole.
Oh, That's super cool. Thanks. You really do know a lot about this. Okay, so where am I? I want to go back to draw now. Okay, so triangle ABD. Jonathan picked out these problems for me. A, B, D equals. Okay, so if this is a rectangle, so if AB is 5, what is this side over here? Someone call it out. I don't care who. Do you know what it is, Les?
Oh, sorry.
5. No, that's good. Perfect. Thank you, Bailey. That's 5. Now, the whole perimeter, we're told, is 34. So how can we figure out what this side AD is? Oh, Alyssa, go ahead. I'm going to ask Alyssa because this is one she knows. How do you do it?
So just add up the 5 and the 5 and it equals 10, and then 34 minus 10 equals 24, right?
Mm-hmm.
And so then you would have to split 24 into 2 equal groups, and 24 divided by 2 equals 12.
Whoa, yes. So Alyssa is, if she knows the answer, I'm going to call on her because she is young and she won't know all of these. But Alyssa says that, so you take the perimeters 34, you subtract 10 for this side and 5 for this side and 5 for this side, you get 24, and then you divide that by 2 and you get 12. Okay, now it wants to know what the perimeter of this triangle is right here. So I don't think Alyssa will know this one. Bailey, do you happen to know if you have two sides of a right triangle, this is a right triangle because we know this is a rectangle, how we find what this one is right here?
No, I don't.
Okay. Jonathan, how do we find out what that line BD is?
It's the Pythagorean theorem is with a right triangle.
Okay.
It's a squared plus b squared equals c squared. And so when c squared is the side that's tilted, the longest one.
Uh-huh.
And so you can say the BA, which is 5, is 5 squared. And then AD is the B squared. And so it's 12 squared equals C squared. So the answer of 5 squared plus 12 squared equals a number in which the square of that is C.
Okay, so what Jonathan was just explaining is called the Pythagorean theorem. It was named after a Greek mathematician named Pythagoras. And basically what it says is that when you have a right triangle, and only when you have a right triangle, if you add the squares of the two smaller sides, it will equal the square of the bigger side. We're not going to go into why that is, simply to say that that is true, okay? Now, a little side note, there are quite a number of perfect square right triangles. In other words, actually there's not quite a number, I think there's 5. But there's triangles where the measurements of the outsides are whole number integers. Okay, so let me give you an example of one. So here is a triangle.
3, 4.
What?
3, 4, and 5.
Right. So these come up in MathCounts all the time. So one of the things that we'll do is I will force you to memorize a number of things because they come up so often. One of them is the sides of the perfect triangles. I'll have you memorize all the squares, perfect squares, up to 120, up to 12 squared. No, actually up to 20 squared is what I make you do. I'll make you memorize all the prime numbers between 1 and 100 because it's just, they come up all the time. And then there's a list of other things I'll make you remember as well. But so let's take this one. So 3 squared is 9 plus 4 squared is 16 equals 20 equals this one squared, which is 25. And in fact, if we add 9 plus 16, we get 25. So that proves that this is correct. Okay. So let's do what Alyssa taught me to do, and let's erase.
Just sort of click on it.
Oh, that's so cool. I love it. Okay, and then we'll go back to draw. Okay, so here we said 5 squared plus 12 squared, 5 squared plus 12 squared equals this number BD squared. So 25 plus 144 equals 169. This is why I also have you memorize the perfect squares up to 20 squared, because if you had, you would immediately know that 169, what the square root of 169 is. As it is, does anyone happen to know what the square root of 169 is? Maybe you don't have it memorized. Maybe you do.
Can I say?
Yeah.
13.
Perfect. Was that Jonathan or Bailey? You were distorted.
That was me.
Okay, so that equals 13. We'll say 13 squared. So let's write right here 13. And lo and behold, if you had been doing math counts with me over the course of several months, you would have already measured. You wouldn't even have to do this calculation, because you would already recognize, I would have made you memorize that a triangle with the sides 5, 12, and 13 is one of the perfect right triangles. You would already know this. As soon as you saw the 5 here, you would already be thinking, this is almost certainly going to be a perfect right triangle. And then when you saw the 12 here, you'd be like, yep, that's right. And then you would know that that side was 13. But if you didn't, you could always use the Pythagorean theorem. So we're looking, now let's ask ourselves again, what is the thing that we're looking for? We're looking for the perimeter of A, B, D. So you say 5 plus 12 plus 13 is 5 plus 12, what? Plus 13. And 5 plus 12 is 17, plus 13 is 30. Yes, does everyone agree with that?
Yeah.
Okay. All right. And then I think we're going to do one more problem. We're not going to do all of the ones that Jonathan picked up. We're going to stick with the ones on this page. And now I have to tell you that I haven't looked over this problem, because it wasn't, I usually look over problems just to make sure I don't do something stupid, but I
It's
might.
an interesting one.
Okay. Harvey has a fair 8-sided die. Okay, so what is an 8-sided die? Well, first of all, in case you don't know, a die is a singular for dice. And it looks something like, you see that dice right there? It's kind of like a weird, it's like 2 pyramids stacked on top of each other, fused at the base. Okay, so on the top pyramid, there's 4 sides, and then the bases are fused, and on the bottom pyramid, there's 4 sides. So there's a total of 8 sides. These dice, if you ever played a game called Dungeons and Dragons or some other games that require 8-sided die, you've seen one of these. Okay, Harvey has a pair, that means 2. Oh, I'm sorry. No, sorry. Take that back. Harvey has a fair 8-sided die that has a different number from 1 to 8 on each side. If he rolls this die twice, what is the probability that the second number rolled is greater than or equal to the first number? Express your answer as a common fraction. Jonathan, you're killing me. Why did you pick this problem? Let me think this through for a second.
It has tons of logic.
I know. Well, let me just think for a second, because I know how to solve this. It's just a lot of work. So I just want to just think real quick. Is there, wait, what?
Sorry. So did the one with the perimeter and using the Pythagorean theorem.
Let me just see if there's a faster way to solve this. I mean, I know how to solve this.
Sorry, Dad.
It seems like an awful lot of work, but we'll figure it out. Let's just cheat and see if there's a faster way. That's all I'm saying. Okay. All right. There's not a faster way. That's fine. Okay, so let's think this through. What's the best way to explain this? Okay, so let's take the numbers on the dice. There's 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so what is the probability that on the first roll I get a 1?
1 out of 8.
1 out of 8. So you know what? Actually, I don't want to get into probability today because we should do some easier probability problems before we
Sorry.
get. That's okay. I know you know.
I picked this one because there was another probability problem that you said was okay.
I know. Well, there's probably an easier probability problem. So what we're going to do is we are going to.
The probability I picked before was pretty easy.
Which is the one you picked before?
It was this: if you have 6-sided dice, what's the chance of rolling it twice the same number?
Oh, that's easy. Let's do that one. Yeah, this one is not a great intro to probability. The one that Jonathan just said is. Okay, so you have a 6-sided dice, and what's the probability of what?
Of rolling the same number.
Twice.
Like you roll it twice.
Okay.
Yeah.
Yeah, this is a very good intro to probability. Okay. Okay. All right. So where was I? Okay. So first of all, we need to talk about probability. So this is, and I wasn't really prepared to talk about this, but I think this is a good time. I just may not explain it in the most concise way because I would have to think about how to do this. Okay, let's start with quarters. Okay, if we flip quarters and we want to know what's the probability, that means what are the chances of us getting ahead if I flip a quarter? So first of all, what are the possibilities if I flip a quarter? I can get ahead or I can get a
Tails.
Right, so I can get a head or I can get a tail. Is it, just Lisa, is it more likely to get a head or a tail or vice versa, or is it the same?
It's the same.
Lisa says it's the same. Okay.
Technically, the chances are a teeny bit more for tails.
Okay. Well, I'm going to ignore that,
100.
but we're going to ignore that fact. Okay. So if the question is, what are the chances I get ahead? Probability is about making fractions. So what you do is you put the total possibilities on the bottom. There's 2 possibilities, either a head or a tail. And then on the top, you put the number of possibilities that accept the condition you're looking for. So I'm going to put a 1 on the top because of the 2 possibilities, heads or tails, the only one that I consider to be meeting the outcome that I'm looking for is heads. So there's 1 outcome that meets the criteria we're looking for out of 2 possibilities. So the probability is 1/2, or another way how we usually say that is we express it as a percentage and we say 50%. Okay. So I'm going to go through this one more time because it will be helpful in the problem we're about to do. So we make a fraction. When we're doing probabilities, we make a fraction. We say what's on the bottom is the total possibility, number of possibilities. That's 2. It can be a heads or a tails. On the top, we put what are the number of possibilities that meet the conditions we're looking for, and that's 1. So my probability is 1/2 or 50%. Now let's do a little bit more complicated problem. Let's say same thing, but now I'm going to flip the coin twice and I want to get a heads the first time. So first time I can either get a heads or a tails. And then the second time I can get a heads or a tails. I'm trying to find out what are the probability that I'm going to get a heads both times. Now, if you are trying to calculate the probability of 2 independent events happening, both happening, you multiply the probabilities of the individual events happening. Okay, so what do I mean by that? What I mean is, I am flipping the coin twice, okay? My outcome on my second flip is completely independent of my output on the first flip. So if I could flip a heads 100 times, and it has no bearing on whether I flip a heads the second time, assuming that the coin is fair. And they'll always tell you in MathCounts that it's a fair coin, it's a fair dice, whatever, just so you don't have to worry about that. But if the probability of me flipping a heads the first time, we've already decided is 1/2, what is the probability of me flipping a heads the second time? It's also 1/2, right? Because every time I flip a coin, the chances of me getting a heads is 1/2. So as I said before, if you have two independent events, here's one independent event, here's the second independent event, and you want to find out what the probabilities of both of them happening, you multiply the probabilities of the individual events. So what I'm going to do is I'm going to say 1/2 times 1/2, and that equals, okay, so to multiply fractions, if you haven't been there for a while, you multiply the tops, which 1 times 1 is 1, and then you multiply the bottoms, and you get 2 times 2 is 4. So the probability of you flipping two heads is 1 in 4. So if you do this experiment a million times, 1/4 of them will come up with heads, heads. Let's see if that makes sense. Okay, so let's list all the possibilities that we can have. So if I flip a coin twice, I can have heads the first time, and I can have heads the second time. Or I can have heads the first time, and I can have tails the second time. Or I can have tails the first time, and heads the second time. Or I can have tails the first time, and tails the second time. So there's 4 possible outcomes. That's kind of what we said before. How many total outcomes are there? That goes on the bottom of the fraction. And how many of the possible outcomes are meeting the criteria we're asking about? Just this one, heads, heads. So there's 1 on the top of the fraction. We put what are the number of options that meet the criteria we're looking for, and that's 1. And on the bottom of the fraction, we say what are the total number of possibilities, and that's 4. So here we calculated the probability 2 separate ways, got the same answer. That tells us we're on the right path. Okay. Now let's do a third problem with the coins. Okay, now we're going to do a third problem with the coins, and then we're going to get to Jonathan's problem with the dice. Okay, what is the probability of us flipping a coin twice and having the second flip match the first flip? Okay, so we don't know what the first flip is. And let's see, how do I explain this? Okay, I've got the way to explain this. So our first flip, we don't know what our first flip is. And here's the point that's important to understand. We just want to know what's the probability that the second flip matches the first. But we don't care what the outcome of the first flip is. In other words, we can flip a heads the first time, and it doesn't matter, it's fine. All we have to do is flip a heads the second time, and we meet the criteria that we've asked about. The 2 flips match. So I'm going to write that here. We could flip a heads the first time, and that's fine. So I'm going to circle it, meaning that's okay. Or we could flip a tails the second time. That's also fine. We don't care if we flip a tails the first time, as long as we flip a tails the second time. So it's not the outcome of the first flip that matters, because no matter what we flip on the first time, it's the outcome of the second flip that matters. Because if we flip a heads the first time, there's 2 possibilities. We can flip a heads, and we can flip the tails. It's not flipping the heads the first time that matters. It's when we flip the second time, are we also going to get a heads? And then the 2 match, and that's okay. And if we flip the tails the first time, that's fine. It doesn't matter the outcome of the first flip, okay? What matters is that on the second flip, when we flip a tails the first time, we can get a heads or a tails. What matters is the second flip, because the second flip has to be a tails. So look, we can get we can flip a tails the first time. As long as we flip a tails the second time, we're fine. If we flip a heads the first time, as long as we flip the heads the second time, we're fine. So let's take a look at that. There's two ways we can calculate this. We can say, well, there's 4 different outcomes. There's 4 different things we can do. We can do heads, 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 tails, tails, heads, tails, tails. There's 4 different possibilities. And there's 2 possibilities. This one, heads, heads. This one, tails, tails, that meets the criteria we're looking for. So that's 2 out of 4, which is 1/2. Now, a faster way to do it in my mind is just to say this. We don't care what the first outcome is. All we care about is the second one. And no matter what we flipped on the first try, whether it be heads or whether it be tails, there's a 1/2 chance that we'll match it on our second one. Because if we do heads the first time, we've got to do heads the second time. There's 1/2 chance we'll get heads the second time. If we do tails the first time, then there's a 1/2 chance that we'll do tails the second. Tails, tails. So no matter what we flip the first one, we don't care, but there's a 1 in 2 chance that we'll match it on the second time. So using this different method of calculation, we also get 1/2, which tells us that since we calculated it 2 different ways and we got the same answer, we're good. So to wrap it up, let's just quickly look at Jonathan's problem. Actually, I'm just going to leave it there. We're going to do Jonathan's problem first thing next time, because we've been going now for 45 minutes and that seems like enough. So again, guys, apologize that I missed you the first time. Hopefully you'll watch this video. I'm going to post it on YouTube. And if you like it, and this kind of seems interesting to you, then you can join us for practices. If you would enjoy doing this kind of thing in competition, you can join us in the competitions. And please don't look at that and be like, oh man, I wouldn't have figured out any of those. Doesn't matter. That's why we're practicing, is so that you can learn to do these. And you know, people do math counts, and the first time they might get 8 or 9 out of the 30 problems, and the second time they might get 15, and by the third time they might be getting 20. No one has ever gotten all of the problems, at least no one I've ever coached. No one has ever gotten none of the problems right, at least none of the kids I've ever coached. So you're going to have some success, and you're going to have some challenges, and you'll learn from every single one of them. Also, last thing I'm going to say is that in addition to the prizes, which are kind of cool, you also, if you make it to state, and you know, my team has always gone to state, or at least some members of the team have gone to state. I don't remember if all my, I think pretty sure all my teams have gone to state at least once. You know, they put you up in a hotel, they buy you some breakfast, they buy you some lunch, and it's just kind of a fun thing. They won't do that this year because of COVID. We'll all be doing it virtually, but that's what they've done in the past, and it's super fun. So thanks for tuning in, and I hope that I will see some of you guys next week. I will, what I'm going to ask you to do is, if you've made it through this video and you think you're interested in joining MathCounts, maybe you can have your parents contact me. My phone number is 541-301-6395, and I think that as long as, like, I can't contact you guys directly, the kids directly, but it seems like it would be acceptable if your parents use their cell phones to contact me, and then we'll put you on a WhatsApp group, and hopefully Miss Amy won't, hopefully that'll be acceptable with the rules. I don't want to do anything that's not okay with the rules. But anyways, happy mathing, and we'll see you next week, hopefully. Talk to you later. Bye.
Thanks, Dad.
You're welcome.